How does circuit depth affect quantum circuits? Imagine trying to run a race where each runner can only move one step at a time, waiting for the previous runner to finish before starting. That's similar to how circuit depth works in quantum circuits. Circuit depth is the number of layers of quantum gates that must be applied one after another to complete a task. Each layer can have multiple gates acting on different qubits at the same time, so the depth counts only the sequential steps, not all the gates. This means that if you have gates working on separate qubits simultaneously, they don't increase the circuit's depth. The longer the circuit runs, the more time it takes to finish. Quantum gates need a certain amount of time to operate, and the circuit cannot move forward until each layer is complete. So, a circuit with a high depth takes longer to execute on a quantum computer. This is important because quantum systems are sensitive and prone to errors. The longer a circuit runs, the more likely it is that errors or decoherence will affect the results. Decoherence is when quantum information is lost over time, which can ruin the computation. Minimizing circuit depth helps reduce errors and makes the results more reliable. If the circuit is too deep, qubits might lose their quantum state before the process ends. This makes the computation less accurate. Hardware limitations also matter. Quantum devices have a limited coherence time, which is how long qubits can stay in their quantum state. If the circuit is too deep, it might not finish before qubits start losing their quantum properties. When building basic quantum circuits, like creating entangled states, different designs can have different depths. For example, creating an 8-qubit Greenberger-Horn-Zeilinger state can be done with a circuit that has 8 layers or one that reduces it to 5 layers. Both produce the same final state, but the shorter circuit is faster and less prone to errors. Quantum programming tools like Qiskit help measure and optimize circuit depth automatically. When preparing a circuit for a specific quantum device, the compiler tries to make it as shallow as possible while respecting hardware constraints like which qubits can directly interact. Sometimes, extra operations are needed to connect qubits that are not directly linked, which can increase depth if not managed well. In the end, circuit depth affects how long a quantum circuit takes to run, how many errors it might encounter, and whether it can be successfully executed on real hardware. Keeping the depth low makes quantum computations faster, more accurate, and more practical. That's why optimizing circuit depth is a key part of designing effective quantum circuits.